Hi there, welcome to your lesson on relations versus functions. Some of these graphs here are functions, some are not. We'll look at that in the coming lessons. All right, let's take some notes while watching this. You're going to learn some key vocabulary for this unit. First, let's begin with sets, relations, and ordered pairs. A set in mathematics is a defined collection of things, and those things are called elements. So a set is a collection of elements. Here's an example of a set. We call it set A. We use this symbol here, these brackets, which are the curly brackets. Those always represent a set of things. So what this means is we have a set of things A, B, C, D. Set B, I've defined as a set of these things, E, F, G, H. A relation. It is a relationship between two sets, so that elements from one set can be matched to elements from the other. So a relation just shows some kind of relationship between two sets. We'll take a look at an example in a moment. Ordered pairs. Ordered pairs are a pair of related elements from two sets, written as xy. I mean, they don't have to be xy, they can be whatever those things are from each set. But commonly, if we write an ordered pair like this, the x represents an element from one set and the y represents an element from another set. Of course, you've seen this kind of thing very commonly used already when you graph points. You have x and y coordinates. Those are ordered pairs as well. But sets do not have to be just points plotted on a graph. They can represent any kind of relationship. So here are some ordered pairs from the two sets above. So if these two sets above here were related, if they were a relation, we could say one ordered pair is AE and another ordered pair is BF, and so on and so on. Okay, let's look at that in an example. So we have an example where set A represents house pets and set B represents number of legs. So there is a relation between set A and set B. Obviously, house pets have some number of legs, so we can show there's a relationship between those two sets. So we can say set A equals, and then the curly brackets, house pets. So that's just defining what it is, and here is in detail listing the elements in that set. So we have set A contains these elements, dog, cat, fish, bird. These are house pets in that set. Set B is number of legs. That's what it is as a definition, but again, listing the elements in that set, we have set B contains the elements 0, 2, and 4. Of course, pets can have 3 legs. If your dog ran in the street and maybe lost a leg, it can have 3, but we're going to assume we only have these numbers in this set. All right, so we're going to map set A to set B. Mapping is when you connect two sets and show the relation. So mapping them, we're going to create ordered pairs. So we have an ordered pair from set A, I'm taking dog, and then from set B, 4 legs. And then another ordered pair, we have from set A, I'm taking fish, and then from set B, I'm saying it has 0 legs. Of course, you can have a mutant fish with legs. That happens as well, but let's use just the numbers in these sets here. We can have another ordered pair, a bird, and it has 2 legs. So we've taken elements from both sets and written them as ordered pairs like this. Okay, a mapping diagram. We've used the word mapping already. A mapping diagram is a specific kind of diagram. It shows how the elements in a relation are paired. Each set is represented by an oval. Let's take a look. So here's a mapping diagram. So here's set A, here's set B. Each one is represented by an oval, and lines or arrows you can see here are drawn to match elements from one set to the other. For example, here, this is our input set, this is our output set, and we say 2 is mapped to 20, or 2 is mapped to 40, 4 is mapped to 40, and so on. It's showing that connection between the sets. Here's another mapping diagram. As I said, it's not always about numbers. Relations and sets can be about anything. So here we have the inputs are 2 people. We have Jorge, Juanita, and there is an output set, and it shows pretzels, chips, and water. So maybe we're showing the kind of snacks they have with them. And Jorge, we can see, is matched to pretzels, while Juanita is matched to chips and a water bottle. Okay, so mapping diagrams can be of 4 main different types. One of them is called a one-to-one mapping situation. We have one element here is matched directly to another element here, and you can see that here. There's another one called a one-to-many. We have one element here matched to perhaps many elements in this set. So for example, this element is matched to or maps to 2 different things here. So we say one thing is matched to many over here. Another mapping diagram situation is we have many to one. So here's many things from this set are matched to a single thing here. So many of these, three of them are all matched to one here. So many to one. And another relationship we can have is many to many. So many to many. You can see this one here, many to, and then on this side also many come into one. All right. So our example with pets and legs, we have here are pets. Here is the number of legs. I've shown the mapping we have. Dog has 4 legs, cat has 4 legs, fish has 0, bird has 2. So there's our mapping diagram. Which of the 4 above situations is represented in our situation? Well, I hope you said it is a many to one situation because dogs and cats both have 4 legs, so we can see many things converging on 1 over here. All right, next. So losing that idea of one to one, one to many, and so on, those mapping diagrams, read these situations here. See if you can sketch a quick mapping diagram that could represent each of these situations, and then describe it as one to one, one to many, many to one, and so on. When picking these here, for example, in the first one, it says students in your class. Don't worry about writing a set of all the students. Just pick a few, like 3 or 4 students in the class, and then in set B, the number of siblings they may have. So your goal mainly is to see these situations, which of these would they be? So let's do that now. Okay, in 1A, we have students in your class matched to siblings. So let's say we have these students right here, and let's say there's a possibility of having 0, 1, 2, or 3 siblings or brothers or sisters. So I have Ivan and Paula with 1 sibling, and I have Ev and Georg with 2. Of course, I don't know if those are the real numbers. I don't know how many siblings you have, but we have this. That the point is that you can have many students with the same number of siblings. So this is definitely a many to one situation. Okay, next one. Trying out this one. Students and mothers. In this case, hopefully your diagram looks something like that. We can have these students, and each student is mapped to a specific mom. You cannot have multiple students with the same mom, or I guess you could, but not in our class. I don't think we have any twins. So we have that situation, and that looks like a one-to-one situation. Okay, next one, try this one. Now we have couples matched to grandchildren. So we have one couple, like a grandma and grandpa, they are a couple, and they have some grandchild over here. And then another child here. So couples to grandchildren. There can be another, so this is actually one to many, because you can have one couple with a grandchild, and that same couple has another grandchild, right? So they can have 2 grandchildren. So it's a one to many situation in this case. All right, let's try this one here. You have a rectangle, and we're looking for area of that. If your input is this x value, the length of the rectangle, then what will be the output for your area? So fill that in. Okay, check your work there. Your areas, for example, if x was 1, then our area will be 1 times 2, an area of 2, and so on and so on. This is one to one. There's a direct relationship here. Each input leads to one output here. How about perimeter with this rectangle? And check your numbers there. Great, so that's mapping diagrams for those situations as well. All right, let's talk about relations versus functions now. We've been talking about relations. Let's talk about now what a function is, because a function is a specific type of relation. So important definitions. Number 1, a relation is a relationship between any set of ordered pairs. Can be expressed as a mapping diagram, a graph, an equation. We've seen that already. So a relationship is any relationship. The domain of a relation is the set of input values. Often these are considered the x values, all right, the independent values. The range is the set of output values. Often these are the y values, the dependent variable. And then we have a function. So this is very important definition. I'm going to highlight it. A function is a specific type of relation. So a function is a relation, but it is a specific one where there is only one output for each input. Let's take a look at that. Here we have some ordered pairs. All right, I'm going to put those in a table. When you put those in a table, you just enter your x values here, and you can put your y values here. So I've just taken those points and put them here. So there's a table of values, easy. You can also show those on a graph. So this relation can be shown on a graph. I just plotted the 4 points. And this relation can also be shown on a mapping diagram, which I know is like kind of the new thing today. So mapping diagram would look like this. We have -2 produces 2, and -2 also produces -2. So we can see -2 leads to -2 and 2 here. So the input here of -2 leads to 2 outputs. And notice that even though we have 4 points, we've only listed 3 here because we don't have to list the repeating ones in the mapping diagram. All right, and likewise, we have an output of 1 here twice, but we only wrote it once here. So there's our mapping diagram. Is this a relation, a function? No, it is not, because we can see the definition of a function was there can only be one output for each input. But here we can see the input of -2 leads to 2 different outputs. So therefore, this thing, it does not represent a function. It is a relation, but not a function. Okay, try the same thing for this one. These steps should be easy. Make sure you have a mapping diagram and then justify at the end. Is this a function? Let's take a look. I didn't show the answers for this. It should be pretty straightforward. Here's our mapping diagram. Take a look compared to yours. And now let's justify. This is a many-to-one situation. Each input leads to only one output. Okay, each input only goes to one output. Therefore, it is a function. This relation is also a function. And it's not a problem that these 2 inputs lead to the same output. That's okay. The point is that each of those only leads to one output. -1 only has an output of 4, and 0 only has an output of 4. So therefore, it is a function. Okay, so these 2. Which one is a relation? Which ones are functions? Both are relations. Which are functions? Okay, check your work now. Okay, next one. Which of these are functions? Okay, and check your work on that one. Next one, which of these 2 is a function? Let's check. First one is only a relation, and the second one is a function. This one is a relation because you can see input of 1 leads to 2 different outputs, therefore not a function. This one is a function. It works. Each input leads to one output. So now it says for the function, which is this one, find this. So this is a certain kind of notation. I hope you've seen this before. This is function notation. It says into the function we put an input of 2. So if we're looking at this function, if our input is 2, what is our output? When it says find f of 2, it means tell us what's the output. When 2 is the input, what's the output? So when 2 is the output is 3. All right, so that's the first one there. How about the next one? When the input is 3, the output is also 3. We can see it here. And then the last 2, 4 and 1. The output here is 4, and the output for 5 is 1. All right, that's simple things about functions. Let's look at another one here. What could this relation represent? Well, it could represent the relation between humans and their age category. Some humans are babies, some are toddlers, some are adolescents, and so on. Justify why this is a function. Okay, it is a function because there is only one output for each input, right? Each input leads to only one output. Great, state the domain of the function and the range. The domain would look like this. For set A, that's our input values, or is our domain. Set A, we have this set of people, that's our domain. How about the range? Well, the range is set B, the outputs, and here's our set for that. And finally, write a function. Well, I'll show you what that means. A function for this could be into the function we put these input values, A, and we get an output value from B. So for example, if our input into the function is Alice, then the output is baby, because Alice is a baby. Or another one, if the input is Pauline here into the function, then the output is toddler. All right, try this one. Take a look at this one together. Here we have Kevin Garnett, a famous basketball player. He played for the Timberwolves team at one time. So this graph shows a bunch of Timberwolves players, because there's different ages here, and the average points they score per game. This one shows just Kevin Garnett, and at his different ages in his career, the average points he has scored per game. What does the first graph represent? Well, the first graph is the average points scored per game for all the players on the Timberwolves based on their age. So we can see, for example, we have 2 players at the age of 28, and they both had different numbers of average points. Second graph represent? Check out this answer. Second one is his average points per game based on his age over time. So which one is a function and which one is not, and why? Well, hopefully you're able to see that. The first one is not a function because we see multiple outputs for a single input. Second one is a function. Please read the answers carefully.